In the last section, we saw new rules for finding derivatives so that we didn't have to use the limit definition and made it much easier, but they're relatively limited. Those are just the basic rules for finding derivatives. Today we expand those rules to something that's called the product rule. So, and also we'll talk about the quotient rule. Well, the product rule is stated this way. I write it out here. And of course, it's the product rule for finding derivatives. If f of x is a function that is actually the product of two other functions. So, for instance, u of x times v of x. Then the derivative of f is calculated using this formula. We take the first function, u, and multiply it with the derivative of the second function. And then we add to that the first function, v, and multiply it with the derivative of the first function. Now, sometimes shortcut notation, we would say f prime of x is simply equal to u times v prime plus v times u prime. We'd forego the x's. And of course, an alternative method of writing this rule is when we don't even have an f function named. That is, we could write it, here's the way it's written with a function f, but we could just say, what's the derivative with respect to x of a product of functions u and v? So the idea is that we have two functions multiplied together. And again, that would be u times v prime plus v times u prime. That is the first function times derivative of the second plus the second function times derivative of the first. Well, let's put this to use with some examples. In the first example, or problem, is this. Let's say example 1. Given that y is equal to the product of 3x squared minus 2x and 4x plus 5, then we are to find the derivative of y with respect to x. Derivative of y with respect to x. That's just the derivative. Now here it's easy to imagine that we have actually a product of two binomials. We can think of the first binomial here as the u of x function. And of course it's multiplied with a second binomial, and we can think of that second binomial as the v of x function. So if we're wanting to find the derivative of y with respect to x, we would use the formula u times v prime plus v times u prime. Once again, first function times derivative second plus second function times derivative first. Now, when we're learning this rule in the very beginning, eventually we'll want to accelerate the way we do our problems. But when we're doing this rule in the beginning, until we feel very comfortable, we just write down the parts. And as first we understand that the u function is that first binomial, 3x squared minus 2x. And you see in the formula, we're going to need a u function, but we'll also need the derivative of u. So we'll go right over here to the right and go ahead and calculate u prime, the derivative of u. And we can see quickly from our basic rules of differentiation that when we take the derivative of 3x squared, we multiply the 2 and the 3 together, and then we reduce the power on x by 1. And then we subtract and we take the derivative of 2x, and of course because that's 2x to the first, we remember that that will just be the constant 2, or that coefficient. Now, we also need v prime, but we also need v. And of course we have to start with v to find v prime. That is, we have to start with the function v, which we identified above as 4x plus 5. And then once we know what v is, and v prime is very easy to calculate here, of course we would get the derivative of 4x, which is just 4, plus the derivative of 5, the derivative of a constant is just 0. And so in this case, v prime is simply 4. And now we have all of the components we need for the derivative, or to put into the derivative formula, the derivative of a product, that is. We'll replace u in the formula with 3x squared minus 2x. And then we'll replace v prime. A lot of times I put the result of a derivative in brackets. V prime we look over and we say, oh yes, v prime we calculated to be 4. And then this plus v, and we remember v was the original function, 4x plus 5, times the derivative of u. And so we'll replace the derivative of u with what we calculated, and that was 6x minus 2. So that's the result we get. And we probably now would do a little bit more algebra, that is, we'd multiply, expand, that is, multiply the pieces out, and then combine like terms. So in the first part, when we're multiplying 4 with 3x squared minus 2x, we'd multiply the 4 and the 3x squared and get 12x squared. We'd multiply the 4 and the negative 2x and get negative 8x. And then we'd have our plus sign, and we'd have to use FOIL in the product of the two binomials. So we'd say that we'd get a 4x times a 6x, which will be 24x squared. And then, of course, we'll have a 4x times a negative 2, which will be minus 8x. And then, of course, we'll have a 5 times a 6x, which will be 30x. And then finally, 5 times negative 2, which will be negative 10, squeezing that in a bit. And then as we go back and evaluate and determine, we see that the derivative of y with respect to x, as we combine like terms, we have a 12x squared and a 24x squared, which is 36x squared. And I see we have a minus 8x and a minus 8x and a plus 30x. Well, that would be, 14x plus 14x. And then finally we have a minus 10. So that would be our result using the product rule. Whoops, using the product rule. Now, this is example, and maybe you were thinking to yourself as we did this problem, there's really an alternative method here. And it would have been it would have been all right to do this, but you've got to remember what we're doing now is practicing the use of this product rule. And there will come a time when we can't multiply the two binomials together. And here's what I mean, is that we could have started, this is the same example, just a different approach. We could have started with y being 3x squared minus 2x times 4x plus 5. And before we actually went to find the derivative, we could have multiplied that out. So we could have used FOIL right now. We'd have the 3x squared times the 4x, which would be 12x cubed. And we would have the 3x squared times the 5x, which would be 15x squared. And the negative 2x times the 4x would be negative 8x squared. And the negative 2x times the 5 would be a negative 10x. And when we combine those terms, I think we get 12x cubed. And it looks like plus 7x squared. And finally minus 10x. Now, if we would have done that first, of course, then calculating the derivative we would do from here. That is, the derivative of y with respect to x is just calculating the derivative of a polynomial. So we'll take the derivative of 12x cubed, which would be 3 times 12, or 36, and then x squared. And then the derivative of 7x squared would be the 2 times 7, which is 14, x to the first. And then, of course, the derivative of minus the derivative of 10x, which would just be 10. And you see that we get exactly the same result, and maybe the second method would have been easier. But once again, we're really trying to practice the use of the product rule. Although we could do it an alternative way this time, that won't be the case in the future. Well, as we continue the study of the use of the product rule for finding derivatives, our second example is the function f of x is equal to 1 over x plus 1 times x minus 1. And we're supposed to find f prime x of x, or the derivative. So as we're thinking through this, let's once again here we're thinking, okay, f of x is this 1 over x plus 1, just really rewriting the function times x minus 1. And if we're thinking in terms of product rule, of course, this is the first function, u, and this would be the second function, v. And of course, to use the product rule, we need to know f prime of x is the first function u times the derivative of the second function v prime, plus the second function, which is v, times the derivative of the first function, and the derivative of the first function is u prime. So we go about plugging the values in again. So we identify u and v and their appropriate or corresponding derivatives. So over here is my support work, and I'm thinking, okay, well, I'm going to make u equal to 1 over x plus 1. Now, I need to calculate u prime, and as I look at that form, that's not a good form for calculating u prime. I'll notice that 1 over x is really the same thing as x to the negative 1, and so that transformation of u allows me to find u prime much easier. So now I'm worried about u prime, and u prime, I'd say, oh, okay, derivative of x to the negative 1, what do I do? Well, I bring down the negative 1 in front of the x, and then I decrease the exponent by 1. Well, if I take the old exponent, negative 1, and decrease it by 1, I actually get negative 2 as a result. So it ends up being x to the negative 2. And of course, the derivative of 1 that I've got at the end, that's just the derivative constant, and that's 0. And so we get u prime is negative x to the negative 2. But we know that we shouldn't really leave things that way. We'll write that as, we'll write that as negative 1 over x to the positive 2 power. And then we need to, of course, identify v, and v is x minus 1, and there's very little work to do here. V prime is simply 1, isn't it? The derivative of x is 1, and the derivative of minus 1, or minus the derivative of 1 is 0. So v prime is certainly just 1. Now, I'm going to pause here, or not stop, but I want to really show you the way we might do this so that we don't get strung out and we're doing things every which way. And we could obviously go now and put in our u value, we could put in our v prime value, we could put in our v value, and we could put in our u prime value, and that would be okay. But I want to show you something that might be a little more efficient for the future. And here's the way I would like you to get used to trying to write these things, because there will become a time when things are convoluted so much that we just have a hard time keeping track of it all unless we know how to write it down. So here's the way I would say this. If we're looking for finding v prime, we have to remember that the way we go about making those calculations is we say the first function times the derivative of the second. That's the first thing we do. Now, let's remember that 1 over x plus 1 is the first function, and we actually wrote it a little earlier as x to the negative 1 plus 1. So there's the first function, and then we'll say times the derivative of the second. So without actually calculating it, we're writing down derivative of second function. Second function is x minus 1. And then we add to that, okay, we reverse the roles. We'll say the second function, which is x minus 1, and then we multiply it with the derivative of the first function. And of course, the first function we said was x to the negative 1 plus 1. Now, again, I want to point out, this is u times v prime that we have here, and this is v times u prime that we've listed there. We haven't done the work, we've just listed what we're doing. And so that will make it easier in the future to write out the directions for our work. So we go back and say, okay, let's actually replace the derivatives. First we have this x to the negative 1 plus 1, and then we'll calculate the derivative of x minus 1. And we saw up above, that's just 1. And then we have our plus sign, and then we have our function x minus 1, and now we multiply that with the derivative of x to the negative 1 plus 1, which we saw just a moment ago gave us negative x to the negative 2 power. That's actually what we got before we put it into a different form. And so, again, now we have some algebra to do for us to complete this, but we can certainly do that now. F prime of x, let's see, when we multiply the 1 out, we'll get nothing more than x to the negative 1 plus 1. And in the case, over here, in fact, let's rewrite this right-hand side, and that's that derivative result negative x to the negative second. Because that's negative, instead of saying plus in the middle, let's say subtract. Let's just make it easier for us to think about. X to the negative 2 times x minus 1. So I shouldn't have put that plus originally, thinking about moving that negative sign to this position. Okay, now we can do that multiplication more readily. Okay, f prime of x is x to the negative 1 plus 1. And then we're going to say negative x to the negative second times x to the first. So negative times positive will be negative. And let's just stop and think over here. X to the negative second times x. What we would do is we would add the exponent negative 2 and the understood exponent positive 1. And of course that gives us an x to an exponent of negative 1. So we'd get an x to the negative 1 power here. And then we have negative x to the negative second times a negative 1. Well, negative times negative is positive, and something times 1 is itself. And so we have just x to the negative second there. Now we look at our expression, and we see that we have this x to the negative 1 and this minus x to the negative 1. So those actually add to 0. And all we have left is 1 plus x to the negative second power. Now, we probably won't leave our answer this way. We'll probably, and of course normally we like to have positive exponents. So we'll rewrite x to the negative second as 1 over x squared. And then we might even see the answers left as a single fraction. So if we're going to add those together, we need a common denominator of x squared. So we'll simply rewrite 1 as x squared over x squared. And we're adding the fraction 1 over x squared. And now we see that we can add those two fractions together. Adding the numerators together is x squared plus 1. And of course we have the common denominator of x squared. So that's a way we could leave our answer, and that would be certainly adequate and acceptable. Now, notice again what I did here. Rather than fill into the formula, I wrote down what I was going to do and then just proceeded and made each of those operations come to life. So let's pause for a moment while I get ready for the next page. Okay, what I'd like to do here is compare by noting the differences. That is, compare the basic rules that we talked about last time with the product rule that we're talking about this time. So if you recall, with the basic rules, one of the basic rules is the product of a constant and a function. And how do we find the derivative of a product and a function? And so that looked like this. If we have a function f of x that's equal to some constant times a function u of x, that the way we calculate that derivative is that we just say, well, the resulting derivative is nothing more than the constant times the derivative of the function. And we got to, and what we're talking about today is called the product rule. Okay, let's compare here. The product rule. In the product rule, it says if we have a function f of x that's the product of two functions. We normally think in terms, we normally think of these functions as having variables in them. And this says that if we want to find the derivative of a product of functions, then we have to use this complicated formula, which is first function times derivative of second, plus second function times derivative of first. much more complicated. Now, comparing the differences in the basic rule, this is a constant, no variables here. See, it's just a number. And in this case, of course, there's variables. So it's a constant times things that have variables in it. In the product rule, both of these things have variables. The first thing we're multiplying has variables, and the second thing we're multiplying has variables. So that's the difference between those two and why we have two different rules. Clear of that. So, you know, a specific example is the idea of compare the process of finding f prime of x and g prime of x given these two functions, okay? So for instance, if f of x is equal to 3 times 2x squared plus 5x, and g of x, you know, look at the difference. G of x, let's say, is 3x times 2x squared plus 5x. Well, in this case, we have to use the basic rule, because that 3 doesn't have a variable portion to it. In the second case, we would have to use the product rule if we were simply using a rule. Of course, in the second case, we could actually multiply it out, the 3x out, before we found the derivative. But let's look at these processes. Let's see how we would actually use the first function, finding the derivative of f of x. And remember, when we have a product times a function, it's a constant times a function. Finding the derivative is the constant times the derivative of the function. And in the case, this function is 2x squared plus 5x. That's what 3 is multiplying against. And of course, that can be done pretty quickly. The derivative of 2x squared plus 5x would give us a 4x plus 5 when we find that derivative. And of course, that simplifies then to, or expands as 12x plus 15. On the other hand, g prime of x, much more complicated. The way we'd have to go through that if we were using the product rule is we'd have to say first function, which is 3x, times derivative of second function. The second function is 2x squared plus 5x. Then it's plus the second function, which is the 2x squared plus 5x, times the derivative of the first function. And the first function is 3x. That's why we write derivative of 3x. And then, of course, as we simplify here, finding the derivative of 2x squared plus 5x, we know is 4x plus 5. And the derivative of 3x, we know, is just 3. And so as we expand and combine, we'd say 3x times 4x, 12x squared, 3x times 5, 15x. Over here, we'd have a 3 times 2x squared, which is 6x squared, and a 3 times 5x, which is a 15x. And when we combine terms, 12x squared plus 6x squared, of course, is 18x squared, and 15x plus 15x, of course, is 30x. So it's a lot more complicated process if both functions are variable rather than having one that is a constant. So I'd like to end this discussion about the use of the product rule by looking at that function f of x we have on the other page. F of x is equal to 3 times 2x squared plus 5x. Now, again, I want you to appreciate that we could do these multiplications in other ways. I mean, we could do these derivatives in other ways. I mean, we could clearly multiply the 3 with the 2x squared plus 5x and then find the derivative. We wouldn't have had to use any special rule except just our basic rules. But I'm wanting you to see the connection on how things would work if we applied our different rules in different ways. And of course, we do have a product of functions here. We could actually call this 3, it is a constant, but we could call it the function u. And of course, this would be the function v. So, and remember the result we got a while ago. Let's recall, this is from the earlier page. Recall that we calculated f prime of x to be 12x plus 15, didn't we? That was on the earlier page. And we just did that using a constant times a function rule to find the derivative. And that wasn't, in fact, there's an easier way of even doing that. I'm getting kind of off track here. But remember, f of x is nothing more than 6x squared plus 15x if we just multiply that 3 out. And so f prime of x can be calculated here real easily. We'd get 12x plus 15, wouldn't we? That's even easier than what we did a moment ago. But let's just right now remember that this is the resulting derivative that we should get. Now, suppose, what would happen if we actually applied the product rule? What would happen if we used the product rule? Well, of course, the product rule is kind of complicated, so we don't want to use it if we don't have to. But let's see in this case what would happen. So remember, f prime of x, if we have a product, is the first function. In this case, that's 3, times the derivative of the second function. So let me just write down derivative of the second function. And then we say plus, and then we take the second function, now this derivative, just the second function, and we multiply that with the derivative of the first function. And of course, the first function is 3, so we'd be saying the derivative of 3. Now, when we look here, the derivative of 2x squared plus 5x we know is 4x plus 5. And over here we have 2x squared plus 5x, and the derivative of 3, well, that's the derivative of a constant. And the derivative of a constant, lo and behold, is a 0, isn't it? Oh, wow. Well, then over here on the left of the plus sign, when we multiply the 3 with the 4x plus 5, we get 12x plus 15. And of course, over here on the right side of the plus sign, we have something times 0. Well, something times 0 is always going to give 0. So we certainly just have a plus 0 there. And so the final result is 12x plus 15, which is the result we should have gotten. We know that. This is just a longer way than was necessary. That's all we're going to do with the product rule today. We'll see that it'll become very, very useful in the future when the only way we have to do finding a derivative is with the product rule rather than multiplying out polynomials. Next, we'll look at the next lesson. We'll look at the quotient rule.